this is the best tribute we can pay to such a great mentor and physicist of the time. So with that, I begin with my presentation. I will be talking about the chapter 2, the nuclear transformations in the radioisotopes and other things, and I will focus mainly on the radioisotopes which are especially used in the medicine, in radiotherapy, nuclear medicine, and PET-CT. This is just to acknowledge the effort of Asad for the series which he has prepared. So I have just shared the poster which he shared with everybody, and this is the recognition of the event. My disclosure statement that I do not have any financial relationship with proprietary entities in producing, marketing, reselling, or distributing healthcare goods or services consumed or used on patients in the past 12 months. I begin with the introduction. Most of the things are here are common and the basic nuclear physics, which most of us are already familiar. So it's just a refresher, and may be going through some slides uh, slightly fast so that we can cover the actual content which I meant to. As I mentioned, the isotopes which are particularly used in the medicine. So to begin with, just some basic information that there are, uh, can you hear me? Asad, if you can confirm.
Yes, sir.
So there are 1500 different nuclides which are discovered, and out of them only 280 are stable. Unstable nuclides are those which we generally refer to as radioisotopes or radioactive material. Most of the stability is attained through nuclear transformations, which we also call the nuclear transmutations in such cases when the nuclei loses their mass for getting the stability. So that is the basic introduction of that. And along with the de-excitations, the grounded state is attained, and this is ended up in the production of daughter. If daughter is not radioactive, it ends over there. But for high atomic radioactive isotopes, the series does not stop and continues after daughter, and we can get granddaughter and uh, so on. So natural sources of radioactivity include heavy elements with long half-lives and the radioactive daughter products of these elements. The total number of nuclei known to date is 103, and with those ranging from 1 to 92 are found in nature, others are produced artificially. Generally, the lead with atomic number 92 is considered as the graveyard for all radioactive isotopes, as there are series which generally all end up at the lead, either 2006, 7 or 8. So that is otherwise it all isotopes with greater than 82 are radioactive. The decay scheme is a pictorial representation of such series of transformation which I will share in coming slides. And unstable isotopes can also be produced artificially by particle bombardment, and that is the one which we are using for our purposes, particularly when we are producing the fluorine 18 or cobalt 60. The process of radioactivity is exponential, and it's a decay process which is governed by the exponential mechanism. And the basic logic is that when you have more, you will lose more. So that is how it happens. And we begin with the zero time where we have the initial activity, and then with respect to the other some parameters, we'll start to look up the decrease in the quantities. The main control which we generally refer to is the decay constant lambda, which has the reciprocal of time units per unit time with reference to the magnitude of decay. It may be in seconds or hours or days or years. A major quantity which we generally refer to while handling the radioisotopes is activity, which is the rate of decay. This is the quantity that is measured by the radiation detector such as GM counter or other things. And it is in fact the product of the number of radionuclides with the decay constant. And as the number of nuclide and activity are proportional, so activity is also can be described as this relation mentioned here as the exponential relation, where A naught is the initial activity and AT is any activity at any time t. The basic SI unit assigned to the activity is becquerel, but it is a very small unit, which is 1 disintegration per second. So for general users, especially in nuclear medicine, we generally use the megabecquerel uh, units, which are 37 megabecquerel are equal to 1 millicurie. This is generally what we use. And in curies and megabecquerel, the relation is again 1 curie is 3.7 10 to the power 10 becquerel. But as I mentioned, practically we today use the units of megabecquerel for describing or prescribing the red doses to the patients in nuclear medicine or otherwise. A very important parameter which refers to the activity is half-life, which describes the time in which half of the activity will be lost. It is given by the relation here as the reciprocal of the decay constant. And you can also see in the relation here where my cursor is, sorry, over here, you can see we can measure activity at any point of time with this reference to the number of half-lives have been passed, and this relation is very important and very useful to use in routine operations. Here you can see one important thing, that the activity is not influenced by temperature, pressure, or other environmental issues. And you can see the common isotopes, cobalt 60, iodine 131, how they decay. For uranium 238, half-life is very long, 4.5 billion years, and it will decay to half in that much time. Cobalt 60 is 5.2 years, and iodine 131 is 8 days. Another parameter which we refer to is mean or the average half-life. Theoretically, it requires infinite time for the complete decay of radioactive sample. So sometimes it is useful to think of an imaginary radioactive source of activity in decaying at a constant rate. And this is how we describe the relation, that total number of disintegrations over a time interval Ta of an imaginary sample is same as the total number of disintegrations for the complete decay. And the relation which we can use for measuring the average half-life is this: Ta is equals to 1.44 times the half-life. This is in fact an important parameter which may also be referred sometimes in brachytherapy for iridium-192 sources. This is a reference graph which we can sometimes use to calculate the average half-life. The dashed line over here is the product of activity and the number of half-lives, and that can give us the area of this area. This product is same as the area under the curve. It's an approximation, but it helps us in estimation the mean half-life. Just for a practical purpose, we most of the time refer that when we have the radioisotope, radio contaminated material or other vials, for example, in nuclear medicine particularly, we dispose them after certain 10 half-lives. And here's the reference why we do it. So you can see, if we have, I have just taken for example the 100 megabecquerel activity, which you can see when it start to decay after 10 half-lives, it drops to about 1. But if in percentages you see, at the 0 time, the activity is 100%, and gradually it's decreasing, but by every half-life, and after 10 half-lives it's almost 0.098, which is less than 1 per, significantly low. And this activity is the one which is considered generally safe for disposal of the radioisotopes material. So it's a very common practice in nuclear medicine facilities that the radioisotopes, contaminated vials, syringes, and other things, they are stored for 10 half-lives. If it's technetium, they are stored for 60 hours at least, and then they can be disposed as a non-radioactive material. For iodine 131, which is again a very common isotope used, is it's 8 days. So after 80 days, you can dispose them as a non-radioactive safe material. And here is the what you can say the mathematical or physical background and basis on which we take that decision. As I mentioned that radioactive isotopes, they decay, and there are three most common radioactive series: uranium series, actinium series, and thorium series. Uranium series begins with uranium-238, which has the half-life of 4.5 billion years. Actinium it starts with uranium-235, and its half-life is again 713 million years. And the thorium, it begins with thorium-232 with the half-life of 13.9 billion years. But interestingly, they all terminate at the stable isotopes of lead with mass numbers 206, 7, or 8 respectively. This is just an example of the uranium series. You can see it begins with uranium-238 and ends at lead-230, 206. So that is how. I'm not going through the detail of all these DKB processes in between. So just to mention, the start and the end of the series are important. I will talk a little about the radioactive equilibrium because it is again the parameter on the basis of which we select the radioisotopes in our daily use for nuclear medicine particularly. And you can see how we define it. When the ratio of daughter activity to parent activity will become constant, we define it as the equilibrium has achieved. And apparently the decay rate of daughter nuclide is generally governed by the half-life or disintegration rate of the parent. Two basic types of equilibrium are there, transient and secular. If the half-life of parent is not much longer than that of daughter, then the type of equilibrium established is called as the transient equilibrium. And if half-life of the parent is much longer than that of daughter, then it can give rise to what is known as the secular equilibrium. Here are the decay schemes. You can see that how they begin. Parent start to decay to daughter, and if daughter is also radioactive, it will decay to the granddaughter with its own decay constant. So general relation for equilibrium is this, that activity of the daughter or ratio of the two is related to the decay constant in this manner. Again, it's exponential. For transient equilibrium, you can see this relation, and this can be transformed into half-lives, and rather than the decay constant, you can simply use the half-lives of the daughters and parents in place of these decay constants. And for secular equilibrium, you can see daughter and parent ratio of decay is almost the same, so it's 1. So these are the ones which we can refer easily. Here is the example of the transient equilibrium, where you can see that parent start to decay and daughter start to build up over here. At a certain point of time, they become in the transient equilibrium, and that is the time when we are capable to use, and this is what we use in the workhorse of nuclear medicine, the technetium-99m. That is how it happens. Molybdenum starts to decay and technetium starts to build up. At a certain time, we start to use when the technetium, we start to elute from the generator, and that is in fact when the transient equilibrium is achieved. And you can see that here is the decay scheme for the molybdenum. It decays to technetium-99m by emitting the radiation which we use as excuse me, in 67 hours it decays to the beta negative emission, and then this technetium-99 and this emits the gamma photons of 140 keV, which are used for imaging, and that decays to the technetium, which has the half-life of about 200 years, 200,000 years. And this is the statement about technetium, that it's melt at regular intervals once transient equilibrium is established. This is the example of secular equilibrium where radon gases, radon decays to the, radium decays to radon. Radium has the half-life of 1600, and you can see the significant difference in the two half-lives, but still you can see this radon decays to plutonium. So that is how the secular equilibrium is achieved, that radon quantity is not really changing, but radium quantity is fixed, but radon is building up, and then they achieve the same activity at a certain time where the ratios of activity become equal to 1. That is when the secular equilibrium is achieved. I will not talk about the modes of radioactive decays. There are alpha emissions, beta emissions, gamma emissions, electron capture, and internal conversions. So the transformations, these nuclear transformations, they are usually accompanied by emission of energetic particles, which may be charged or neutral. Even they may be photons, which we call as the gamma rays. So the radioactive decays resulting in the emitted particles are shown here. When alpha decay occurs, alpha particles are emitted, which are the helium nuclei. When beta positive decay occurs, positrons are emitted and neutrinos. With beta negative decay, negative particles, electrons are emitted with antineutrinos. In electron capture, neutrinos are emitted. In pure gamma decay, only photons are emitted. In internal conversion, orbital electrons, and along with the characteristic X-rays are produced, and in spontaneous fission, the fission product and some energy is emitted. But as in any other transformation, here again, some conservations are essential, and the conservations are total energy conservation, momentum conservation, charge conservation, atomic and number conservation, and atomic mass number conservation. So these conservations ensure that processes are following a particular mechanism. Modes of radioactive decays, they in fact are, you can see that whenever decay occurs, some energy is emitted, which is mentioned here as Q. And you can see that we can calculate those values with the help of the rest masses of parent, daughter, and the particle which is emitted, or the radiation which is emitted. So it's easy to calculate. And Q is what we call the disintegration energy. It ranges from 4 to 9 MeV for naturally occurring radionuclides. Here is the example of del alpha decay, where a proton, where a parent decays to the daughter with losing 2 protons and 4 neutrons, and helium is released along with the disintegration energy Q. Here radon is shown, radium is shown, which decays to radon through alpha decay, and you can see that that change brought a new isotope. Radium is changed to radon, and this is in fact the major difference, that radium, why we call them the transmutation process, because the isotope is changed. Radon with 88 protons is changed to radium from 88 protons is changed to radon with 86, with some emission of the energy Q energy, which is 4.9 here. Beta negative decay, here a neutron decays into a proton and an electron, but because the angular momentum does not match between electrons and the nuclei, so the nucleus throw out the electron, which is emitted as the beta particle. It's simply the electron with high energy and emitted from the nucleus. Its origin, which describes it as the beta negative, otherwise it's the same electron that we have outside the nucleus. So in beta negative decay, the neutron decays, proton exists within the nuclei, and electron is thrown out. And here is an example that cobalt 60, it decays through the beta negative decay to nickel 60 with emitting some Q energy. And here is the decay scheme you can see. Again, cobalt 60 is the one which is most commonly used in radiotherapy. And these are the transitions which are gamma rays, which are commonly used for the radiotherapy purposes. Then beta positive decay. Here, a proton decays into a neutron and a positron. Again, as the new angular momentum of the positron and nuclei does not match, so the positron is thrown out and neutron is kept is stayed within the nucleus, resulting in increase in the neutron number but decrease in the proton number, which is shown over here. That proton decays, so the parent decays with losing one proton, so Z decreases to Z minus 1, but A remains same because here the composition is different, that this A is Z plus 1 whereas Z plus N, whereas this A is Z minus 1 plus N plus 1. N is the number of neutrons, so the number of neutron is increased and the number of proton is decreased, but the sum remains same as A, and this positron is emitted. This is the energy which you can see. These are some very common examples of this positron emission: nitrogen 13, potassium 40. To our interest, fluorine 18 is more important because that is the most common isotope used for PET scanning in multiple procedures for cancer diagnosis and follow-ups and in cardiac procedures and other. So this is one example of the nitrogen 13 decaying through beta positive decay to carbon 13. And here you can see that this nitrogen with 7 protons decreased to carbons with 6 protons with same number of the mass nucleon number. So that is how this decay is occurring. As I mentioned, that positron emitters are those which are commonly used in PET scanning. And here what happens, the positron is emitted by the isotope, which is combined or annihilated with the electron in the environment, and their combination, the annihilation process, that results in production of two photons of exactly same energy traveling exactly in opposite direction. And these are the photons which are coming out of the patients and they are used for imaging in PET scanning. And the significance of this energy is that the photons with this energy appear because both positron and electron, they have the same mass, and when their masses are converted to energy, each proton and electron, this positron and electron gives this energy to make the photons available. Another is the electron capture. Here beta positive decay is energetically possible if nuclear mass energy difference between parent and daughter is more than 1.02 MeV. And if not, electron capture will occur. And here mostly the in most inner shell electron, the K shell electrons are captured, and the capture of that electron accompanies with the production of the characteristic X-rays. This happens because when electron in the K shell is removed, a vacancy is produced, and that vacancy can be filled by any other high energy level electron. So when electron falls down, it emits the radiation, and they are the characteristic rays. So this production of this happening of electron capture results in the characteristic X-ray production, and the character along with those the Auger electrons are also produced, and this may be thought of as internal photoelectric effect. This is an example of electron capture. Here you can see that again this number of proton is decreased because one electron is absorbed, which neutralizes sort of the proton, and number of neutron is increased, and this accompanies the gamma rays. So this is how this happens. The mechanism is shown over here. The scheme is this, that proton in the nucleus combines with the electron, neutron is produced, and that has results in the reduction in the number of protons and increase in the number of neutrons.
Sir, we can't hear you.
Yes, I cannot hear you.
I think your video is also stopped.
Can you hear me now?
Yes.
Yes, yes.
Okay.
In the
Sorry,
previous
I
slide,
don't
in
know
the
what had
previous
happened.
slide also it was not. I can't hear you.
Oh, oh, okay. I thought nobody mentioned, so I just continued. So we were just talking about the gamma decay, and this is in fact the mechanism through which we get the radiation in nuclear medicine from decay of molybdenum to technetium-99m, and from technetium-99m we get the 140 keV photon. This is in fact the transition of or the production of the gamma rays due to the decay of the technetium-99m to technetium-99 only by emitting the gamma photons with half-life of 6 hours. And this is in fact the common isotope which is used in nuclear medicine for imaging. Another mechanism is internal conversion, and the nuclear de-excitation energy is transferred to an orbital electron, usually the K-shell electron. And the electron is emitted from the atom with a kinetic energy. Here again, actually, this happens because after the transmutation processes, that is the alpha or beta decay, the nucleus has some energy, not sufficient enough to emit a particle, but sufficient enough to emit a photon. And that photon is when ejected, that can produce the ejection of the electrons of that atom, and that is in fact what we call about talk about as the internal conversion. And here you can see that results in ion the positive ionized atom and an electron. This is an example in that regard for cesium-137, which has the half-life of 30 years, and it decays through this mechanism to barium-137.
No sound, sir. Again, your computer is hang, I think. Mansoor sir?
Hello.
Hello. Yes, now we can
Hello.
hear you.
Hello. Hello.
Yes, we can hear you, sir.
Okay, can you hear me now?
Yes.
Okay, okay, okay. So the next process is spontaneous emission, spontaneous fission. In fact, we also call it this emission, spontaneous emission. The process is that actually, when we talk about fission specifically, it is the nuclear reaction which happens between a neutron and a heavy particle. And in nuclear reactors, the neutrons are purposely bombarded, whereas in this spontaneous fission, the neutron the nuclei interact with a neutron with a very small number, and this happens. But this is not sustained because the critical mass is not achieved. So it happens at a small localized level, but it can happen. And so it is again a spontaneous fission which is generally occurring, but it is not common. Examples are here that uranium-238 decays both by alpha decay and with spontaneous fission, although probability of the later is a factor of 1 million times less. So this is very, very rare, very uncommon. Now I talked a little about the nuclear reactions. I will not talk about every reaction in detail, but just for the completion of this presentation, I have shared with the common reactions, the alpha and proton reactions, the alpha and neutron reactions. The mechanism is that
No sound, sir.
the mechanism is that we have a target nuclide which we bombard with some projectile particle. As a result, a particle is emitted, which we call the emitted particle, and that results in the production of our product isotope. So that is the nomenclature, that target is bombarded with a projectile, which results in the production of an isotope with a small particle in production. All nuclear reactions are the same. The difference between nuclear reaction and chemical reaction is that in chemical reactions, the atoms combine with each other or with other elements, and they make molecules and compounds, whereas in nuclear reactions, a new element is formed. For just example, one example is here with alpha and proton reaction, that alpha particles are bombarded on neutron 7 on nitrogen, and that result in the production of oxygen and hydrogen. So hydrogen is generally considered as the proton. So that is how this reaction occurs. Another example of these reactions are alpha neutron reactions. Alpha neutron reactions are those in which alpha is bombarded and neutron is produced. One example is this, that barium is bombarded with alpha and neutron is produced along with the carbon. Another example is the production of gamma rays when neutrons are bombarded, and there are many examples here you can see. With cobalt 59, when it's bombarded with neutron, gamma rays are emitted and cobalt 60 are produced. Gold 197, when bombarded with neutron, it produces cobalt gold 198 and gamma rays, and iridium 191, which is bombarded with neutron, that produces the gamma rays and iridium 198, and this is the one which we use in brachytherapy with the half-life of about 74 days. This is the reaction which is carried out in the cyclotron to produce the fluorine-18 proton-neutron reaction. Here protons are bombarded on oxygen 18, and as a result fluorine-18 is produced with a neutron. This important reaction occurs in the cyclotron, where hydrogen gas is used as a proton producer, and they are accelerated. Those hydrogen nuclei are accelerated in the cyclotron, and they are bombarded on the oxygen 18 atoms, nuclides, and that reaction produces fluorine 18 and neutron. And due to this production of these neutrons, which are generally thermal neutrons, the radiation safety of cyclotron includes the taking care of neutron flux as well. Then another nuclear reaction which is generally carried out in nuclear reactor is the fission process, where a heavy nuclide is bombarded with neutrons, which results in the production of fragmented particles and neutrons. And to sustain a critical mass and chain reaction, we have to have a certain quantity of the neutrons and a certain mass of the target. So that is in fact a very common process which is carried out in a very, very highly controlled environment in nuclear reactors. So cesium-137, which is commonly used in blood irradiators in hospitals, that is also produced by the similar fission reaction. Photo disintegration, where gamma rays are absorbed and neutrons are produced, that process is also happening as a nuclear reaction. So high energy photons interact with atomic nuclei and emit one or more nucleons. This is called the photo disintegration. And on the various reactions, the same gamma neutron reactions, those in which neutrons are emitted are the most common. For the gamma neutron reactions to proceed, incident photon energy must be greater than the so-called threshold energy, which is 8 MeV for most of the nuclei. And the process is inelastic, just like, and unlike the photoelectric effect, Compton effect and production, it does not produce directly ionizing radiation, that is the electrons or other charged particles. So it is significance in contributing to absorbed, it's not the high, the significance is not very high in the radiation dose to patients in radiation therapy. That ends the lecture, and I have just taken these key points from the chapter 2 of Dr. Faiz Khan, and just to ensure that most of the things are covered. So we have talked about the radioactivity, the mechanism, how the radioactivity is happening, what parameters are used, and you can see in current values, the activity of 1 gram of radium is 0.97. Historically, it was one theory was considered as the activity of 1 gram of radium, but now in current parameters existence, the 1 gram of radium is equal to 0.975 MCI theory of radioactivity. Then we talked about the radioactive equilibrium, the transient and the secular, and we see that transient equilibrium is important when we are using the isotope for the nuclear medicine patients. Then we talk about the modes of decay, alpha, beta, gamma, and internal conversions, and we see how the processes are occurring and how they are influencing different activities. Then we talk about the nuclear reactions and how the values are produced. The I acknowledge, I have purposely not written the names because there are many. So at the first place, I acknowledge Mr. Asad Yusuf and the team, Mr. Abdul Qadir, Zaim, and Saad for making this activity happen, and to the MTF and to the all facilitators and participants who have participated in this activity. And I really acknowledge the book Dr. Faiz M. Khan, which helped me preparing this lecture. So I'm thankful for your attention. Thank you.
Thank you very much, sir. We can now take the questions. If anybody have any question, they can